Good morning, one and all.
Good morning, ma'am.
Good
Morning,
morning,
ma'am.
ma'am.
Good morning, ma'am.
Um, Good morning, ma'am.
Guys, my screen is visible.
Yes, ma'am.
Yes,
Yes, ma'am.
Yes, ma'am.
My voice is clear.
yes, ma'am.
Yes, ma'am.
Okay. Shall we proceed?
Yes, ma'am.
Yes, ma'am.
Only 29 students have joined. Okay, I shall start. So, in the last class, we started with the temperature effects. We had discussed the temperature effects with respect to semiconductor diodes. Under that, we have power versus temperature, forward voltage versus temperature, reverse saturation current versus temperature, and then the dynamic resistance relations with respect to temperature. Here, I have given the equations along with the VI characteristics, how the temperature varies with respect to voltage. These 2 points to remember with respect to voltage, as the voltage, the forward bias voltage increases, the temperature, it shifts left at the rate of 2.5 millivolts per degree centigrade. Coming to reverse saturation current, it doubles for every 10 degrees Celsius rise in temperature. So this is the respective equation I gave you. Along with that, the power characteristics, power versus temperature relation. Power decreases, or I can say that power and temperatures are inversely related. And here the slope, whatever you get, that we call it as derating factor. Okay, and the okay, derating factor, these things I discussed, and then okay, and this one we had also discussed the derivation for dynamic resistance, that is 26 millivolts divided by ID. Okay, and apart from that, yeah, only this much. Is the LHS approximately equal to 11,400?
Yes, ma'am.
Yes, ma'am.
That is equal to e power Vd divided by 0.064. Did you get this?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay.
Yes,
So
ma'am.
how do you solve? What is the next step? What is the next step?
Log on both sides.
Log, ma'am.
Yes. Apply. Correct. Apply natural log on both sides. Apply log on both sides. And then solve. In your calculator, you can find ln. ln, you can find ln in your calculator. Please use that. So this would be, if you apply natural log, you will get 9.3414. Make sure that after decimal, some four places you consider. Okay, so that you'll get accurate results. This is Vd divided by 0.064. So if you cross multiply, you'll get Vd. This is approximately equal to 0.6 volts. Yes, Pavan, you are right. It is 0.6 volts. Done? Anybody has got doubt?
No, ma'am.
No,
Shall
ma'am.
we proceed?
Yes, ma'am.
Yes, ma'am.
Bhuvan,
Yes, ma'am.
shall we proceed?
Yes, ma'am.
Abhishek, Anirudh, Aryan.
Yes, ma'am.
Yes, ma'am.
Okay.
No doubt.
Okay. Next question. Next question. For a silicon diode, make a note. For a silicon diode at a working temperature of 25 degrees Celsius, the forward voltage, I'll mention it as Vd. The forward voltage applied across the diode is 0.5 volts. Determine the forward current. They're asking you to determine the forward current. I'll mention it as ID. If the reverse saturation current, that is IS, equals 10 nanoamperes, and they're giving eta value, assume it to be equal to 2. Assume eta value to be equal to 2. Yes, quickly you solve and get me the forward current value.
Zero 0.031.
No. Please check once again. Please don't hurry. Keeping calculators in your hand, please don't do mistakes.
Ma'am, what do we have to find?
Determine ID.
Okay, ma'am.
$11? No, 1.01.
No, please check once again. You can ignore -1 since we are dealing with forward bias. Silicon diode is forward biased. You can ignore -1 or you can consider it as your choice. That does not matter. Okay, well, the one value, it is very small, so it does not matter. So this is 10 into 10 power minus 9 e to the power. Vd value is 0.5 over eta value is 2 multiplied by Vt value. They have given the temperature as 25 degrees Celsius.
26 millivolts.
So this is 26
0.026.
millivolts. 0.026. Okay. E power value, how much you'll get? Can anyone tell me? This power value is this
E power
9.7352?
5 almost. It'll be close to
Huh?
5. Yeah. It'll be close to 5, like 4.9 something. Oh, no,
Which
sorry.
one?
96.
9.7 itself, yeah.
Huh? E to the
9.7.
power value, is this correct, no?
Yeah,
Okay.
it's correct.
Ma'am.
Why
Okay,
do we
okay,
take
fine. Okay.
millivolts instead of taking 10 to the power
What
minus
is your question?
Ma'am,
Yes,
why do we
Omisha, tell me what is your question?
Ma'am, why can't we take 10 to the power minus 3? Why do we write millivolts?
That is what? Milli means 10 power minus 3. I just wrote, you have to solve. You have to consider it as 10 to the power minus 3 and solve.
Okay, ma'am.
I just wrote it as millivolts. You want me to write 10 power minus 3 there?
No, ma'am, it's okay.
If you want, I will write. I thought you people will write and solve. Okay, I'll write 26 into 10 power minus 3. Okay.
Ma'am, power we get 9.61 or 9.7.
Now please check once
Yes,
again.
ma'am. Ma'am, even I got 9.61.
Ma'am, even I got
9.9.65.
Okay, 9.61 is it?
Yes, ma'am.
615.
Yes, ma'am.
Okay. Okay, okay. Proceed.
Ma'am, we'll get 26.1 into 10 power minus 8.
Now please check once again. No, e to the power, how you will type? E, just type e in the calculator and type the respective value, 9.61. Power and all will not come. Don't type power and all. Exponential of.
Ma'am, we get 14,912.
Such a big value. There is no milli, is it?
0.14 milliampere.
Correct, correct. That is the answer. 0.14
149.
149 milliamperes. Since we are dealing with forward current, you have to represent in milliamperes. Is it over?
Yes, ma'am.
Next question. A germanium diode draws 40 milliamperes with a forward bias of 0.25 volts. The junction is at room temperature. Of 293 Kelvin. They're asking you to calculate your saturation current IS and assume beta value to be equal to 1. Solve and tell me how much you'll get. Yes, what is the answer?
Just a minute, ma'am. One second.
Zero point zero four four.
No, please check once again.
Two point oh one times 10 to the power of minus 6.
No, come again. I'm not able to get
2
it.
microamps.
2 microamperes.
Yes.
Is it? Okay. Others?
Yes, ma'am. We close to some 2 microamperes.
Close to 2 microamperes? I got 1.82 microamperes.
Yeah, sorry, 1.82 itself.
Correct, no? Yes. So I'll write the answer here. 1.82 microamperes. This is the answer. Others, please check.
Ma'am, I got 3.9.
No, 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 no. You should get nearly 1.82. If it is approximately, if it is near to this, then we will accept 3 point. That is, no, we will not get that much. Check your calculations once again.
Yes, ma'am.
Okay, fine. We shall proceed. Take down. Next, we will solve numericals on temperature effects of PN junction diode. Okay, take down fourth question. Find the maximum forward current. Find the maximum forward current at 25 degrees Celsius and 65 degrees Celsius of a diode with 600 milliwatt maximum power dissipation at 25 degrees Celsius and a derating factor of 5 milliwatts per degree centigrade. Watts per degree centigrade. Usually this slope we will consider it to be equal to P by T, right? Delta P by delta T. So the SI unit for derating factor would be watts per degree centigrade. Okay, assume the forward voltage drop. Assume the forward voltage drop is constant at 0.6 volts. This is the given question. First you read the question. So they have given T1 to be equal to 25 degrees Celsius, T2 to be equal to 65 degrees Celsius, Derating factor is 5 milliwatt per degree centigrade, and they have given power at temperature T1, right? Power at 25 degrees Celsius they have given, that is 600 milliwatt. Okay, they're asking you to find the forward current at 25 degrees Celsius as well as at 65 degrees Celsius, that is at T1 and T2. Okay, first let us find at 25 degrees Celsius, that is at T1. Okay, I'll take this as IT1. So the relation between power and current is that I, you can write it as PT1 divided by V, where V is constant here, that is 0.6 volts. So PT1 is 600 milliwatt, and this is 0.6 volts. How much you'll get? How much you'll get?
1 watt. No,
1
1
ampere.
1 ampere. 1 ampere.
1 ampere. Is it 1 ampere?
Yes, ma'am.
Okay. Did you understand? Till this step is clear.
Yes, ma'am.
Others, please respond. Sinchana.
Yes, ma'am.
Siraj.
Yes, ma'am.
Siraj.
Yes, ma'am.
Okay. Next. Next step is we shall find power at temperature T2. What is the relation? Nidhi, can you tell me the relation?
PT1 minus delta T into D.
Yes, it is PT1 minus T2 minus T1. T2 minus T1 is nothing but delta T multiplied by the derating factor D. Yes. Substitute and get me PT2 value.
Ma'am, then why did we need current in T1?
They're asking, that is the question, right? They're asking to find the current at T1 as well as T2,
Okay,
at
okay.
25 as well as at 65 degrees
Yes, ma'am.
Celsius. Correct.
Ma'am, 0.4.
Correct. I can write this as 400 milliwatt.
Yes, ma'am.
Since the power at temperature T1 is 600 milliwatt, I shall represent this as 400 milliwatt. Okay. Next.
Yes, ma'am.
Let us find the next forward current, that is at IT2. This is at 65 degrees Celsius. So IT2 is nothing but PT2 divided by V. Substitute and get me the value. Pranav Mishra, how much you'll get?
Yes, ma'am.
0.67 amperes.
Correct. So I can write this as 667 milliamperes. Getting? This is the solution. Any doubts? Samir Kulkarni?
Yes, ma'am.
Did you understand?
Yes, ma'am.
Okay, we shall proceed. Find the maximum power which can be dissipated, which can be, yeah, tell me.
Ma'am, in the previous question, IT2, power is 400 milliwatt, right?
Correct.
And so 400 milliwatt by 0.6. So won't that just be 4 by
Yes, ma'am.
0.6?
6.67, right?
Is it 6.67? No, please
Yes,
check
ma'am.
once again.
Yes, ma'am. It's 400 milliwatt divided by 0.6. So
400 into 10 power minus 3
yeah.
divided by 0.6. Please
0.6.
solve this and get me the answer. How much?
667 milliampere only.
6.67.
6.67.
6.67 milliamperes. Correct? Is it right now?
Yes, ma'am. That's what even I'm at.
Okay, fine. So that is the reason you solve, and if anywhere, if I do any mistakes, please let me know. Fine, proceed. Next,
0.67
find the
milliamp.
maximum power which can be dissipated at which can be
6.67
dissipated. Come again, someone is calling. Satya,
It's
tell
not
tell
6.67
me.
milliamps. It's actually 0.67 amps, like the exact value. It's not 6.
Yeah, it's 667 itself.
Yeah, it's the
667,
previous
so that
one.
will be 6 point. Huh?
The previous answer which you wrote was correct.
Come
667
again.
milliamps.
Ma'am, the previous one, 667 milliampere, was correct.
Yes, ma'am. The actual answer is 0.67 amps.
Why so much confusion to convert from decimal value to milliamperes? Okay, tell me the actual
Ma'am,
value,
it's correct.
Satya.
It's 667 milliamp.
0.666.
0.6. How much?
667 milliampere. 0.67 ampere. 2 by 3 ampere.
0.67 amperes, is it?
Yes, ma'am. Correct.
Yeah.
0.67 amperes.
Yes.
Okay. Guys, further, if you find it difficult to convert from amperes to milliamperes, don't worry, keep the answer as it is. $667 milliamperes. Actually, this is textbook question and this is the answer given. This is what I feel. So, proceed. Find the maximum power which can be dissipated which can be dissipated at 80 degrees centigrade in a diode with a 1 watt maximum power dissipation at 25 degrees centigrade and a derating factor of 4 milliwatts per degree centigrade. Solve this and get me the answer.
Ma'am, what is that? With a 1 watt max power?
Maximum power dissipation.
Okay.
0.78.
Just a second, let me verify. Yeah. So PT2, 780 milliwatts. Shall we proceed? Next question. Find the maximum temperature at which a diode with a maximum power dissipation of 1000 milliwatt at 25 degrees Celsius, the average forward current of 500 milliamperes is flowing through the diode. Assume the forward voltage drop is equal to 0.8 volts, derating factor 10 milliwatt per degree centigrade. Find the maximum current at 75 degrees Celsius. Solve this. So here you have two questions. First sub question is to find the maximum temperature. So the next sub question is to find the maximum current at 75 degrees Celsius. Guys, how much did you get? T1 they have given, T2 you have to calculate by using the relation PT2 equals PT1 minus T2 minus T1 into D.
Is it 85 degrees?
Correct. So first sub question is to find the temperature T2. Answer is 85 degrees Celsius. Anybody has got doubt? You want me to solve?
Yes, ma'am. Solve it. Ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Coming to first sub question, T1 they have given, that is 25 degrees Celsius. Your job is to solve for T2. Okay. So now PT1 they have given, that is 1000 milliwatt. Current, it remains to be same, that is IT1 and IT2. At both the temperatures, current remains to be same, that is 500 milliamperes. Okay. And even the voltage remains to be same, 0.8 volts. And the derating factor, they have given it to be equal to 10 milliwatts per degree centigrade. So use the relation PT2 equals PT1 minus T2 minus T1 into D. Substitute and you have, okay. So first you need to find, okay, PT1 you have, find PT2. Find PT2. You have current and voltage values. IT2 multiplied by V, that is 500 milliamperes multiplied by 0.8 volts. How much you'll get PT2 value? And then you substitute in this equation, PT2 equals PT1 minus T2 minus T1 into D. Using this relation, find T2. Get me these answers quickly. Vaibhav Shetty. Shashank.
Is it 500
No, I don't have answer with me. You have to tell me the answer.
Yes, ma'am. 85.
Others?
85.
85 degrees centigrade.
Celsius.
Yeah,
Yes,
this
ma'am.
is the answer. For temperature answer I have. How much is PT2?
PT2 is 400
400 milliwatts.
400
milliwatt.
milliwatts.
Milliwatt.
Okay. So this is your first sub question. The second sub question is that, okay, in second sub question, you have to find maximum forward current. That is IT2. Solve for IT2. Considering temperature to be 75 degrees Celsius. That is what they have given. First you find PT2 and then you find IT2, that is PT2 divided by V.
Ma'am, will it be find in milliamps itself?
Yes, ma'am.
It is not milliamperes, it is milliwatts, right?
No, the current is in ampere.
No, current value will not get 500
No,
milliamperes.
sorry. Yeah, power is in
1.12
watts.
ampere.
It's in watts.
Huh?
It's in watts itself. Watts.
500 milliwatts you'll get.
Yes.
1.12
Current, how much?
ampere.
No.
Ma'am, 625
625
milliamperes.
milliamperes.
625 milliamperes is the answer.
Yes, my bad.
Others, please verify.
Yes, ma'am. Yes.
Yes, ma'am. 625 milliampere.
Getting? Okay. Shall we proceed?
Yes, ma'am.
Samir Kulkarni, is it done?
Yes, ma'am.
Pramod?
Yes, ma'am.
Okay. Okay, next question, 7th question. It is required, even this question is from textbook. It is required to operate a silicon diode with a forward voltage drop of 0.6 volts at 25 degrees centigrade with a constant forward current up to 100 degrees centigrade. Find first sub question. The forward voltage drop at 100 degrees Celsius. Second sub question. Dynamic resistance at 25 degrees centigrade and 100 degrees centigrade if the forward current is kept constant. If the forward current is kept constant at 26 milliamperes. First you list the parameters whatever you have. So what equation do you use now? What is the equation you'll be using? May I know what relations do you use now?
VFT2 equals VFT1
Correct,
plus
correct.
delta
Voltage
T.
versus temp. Yeah, now correct. It is voltage versus temperature relation. Coming to first sub question. VFT2 equals VFT1 plus T2 minus T1 into V. Here I have written plus. Okay, this in this equation, basically this equation you'll get plus because V value is negative. So here plus into minus if you take, you'll get minus. Make sure that you substitute the voltage temperature coefficient value that is negative, that is minus 2.5. Okay, so this is 600 0.6 volts. This is 0.6 plus T2 minus T1, that is 100 degrees Celsius minus 25 degrees Celsius. Small v value is minus 2.5 millivolt per degree centigrade. They will not give this value in the question. This value somehow you have to remember. That is constant value, voltage temperature coefficient.
Ma'am, when they say forward voltage drop, how do we know whether if it's VFT2 or VFT1?
No, they have given no at 25 degrees Celsius. At temperature, they will mention the respective temperature. With respect to that particular temperature, that is the forward voltage.
Okay, ma'am.
Zero point 4125 volt.
Yes, ma'am. 0.4125 volt.
0.4125 volts, correct?
Yes, ma'am.
Okay. Okay. Second sub question to find RD. RD at room temperature, what is the equation? 26 millivolts divided by ID. That is at room temperature, that is at 25 degrees Celsius. How much you'll get? And next step is at the next value is 100 degrees Celsius. At 100 degrees Celsius, what is the equation for RD? 0.026 divided by ID multiplied by T plus 273 divided by 300. So find RD value with respect to T1 as well as T2. Yes, how much is the answer?
1.243.
How much?
Yes, ma'am. 1.243.
At 25 degrees Celsius, what is the answer?
1
1
1 ohms.
ohms.
At 100 degrees Celsius,
1.25.
1.25 ohms. Is this right? Is this correct?
Yes, ma'am.
Okay. Others? Medhavi. Are you solving?
Yes, ma'am.
Okay. Shall we proceed? Next question. I'll give you 3 homework problems. Solve that and come to the next class. 8th question. A germanium diode, please copy the question. A germanium diode has a forward voltage drop of 0.3 volts at 25 degrees centigrade. Find the maximum and minimum levels of forward voltage drop over the temperature range of 10 degrees Celsius and 10 degrees Celsius. To 80 degrees Celsius. Second sub-question. Find junction dynamic resistance. What do you mean by junction dynamic resistance? What do you mean by junction dynamic resistance? Okay, listen. Junction dynamic resistance is nothing but you'll have to find the dynamic resistance if it is apart from room temperature. See, they have given 10 degrees Celsius and 80 degrees Celsius. If it is apart from other than room temperature, then we call the dynamic resistance at junction temperature or junction dynamic resistance. Or the other name is ambient temperature. We can also call it as ambient temperature or junction temperature. If it is other than room temperature. Okay. Please copy the question. There is one more question. Or take a photo of it. If you are not able to copy, and you please take a photo of it.
Ma'am, could you continue the next question? Done copying.
Okay. Next question. The maximum power dissipation of a silicon diode with a forward voltage of 0.9 volts is 1.5 watts at 25 degrees Celsius. Derating factor they have given to be equal to 7.5 milliwatts per degree centigrade. Question here is to find the maximum current. Find maximum current at 25 degrees Celsius and 75 degrees Celsius. Find forward voltage at 75 degrees Celsius. Next, find dynamic resistance at 25 degrees Celsius and 75 degrees Celsius. If the diode forward current is 20 milliamperes. Done. One more question is there. Which class you have now? Take a photo of it. Next question. A diode with a 700 milliwatt maximum power dissipation at 25 degrees centigrade has 5 milliwatt per degree centigrade derating factor. If the forward voltage drop remains constant at 0.7 volts, calculate maximum forward current at 25 degrees centigrade and 65 degrees centigrade, respectively. Have you copied the question?
Yes, ma'am.
Yes. So tomorrow before attending the class, make sure that you solve and come. We will discuss the answers. Okay?
Ma'am, Shreyansh is not attending this session because he's on a flight. He told me to inform you about that.
Is it?
Yes.
Okay. Any questions with respect to today's class? So please go through once again whatever we have done. Further, if any doubts, you can ask me anytime. Okay? Yeah, we'll wind up. Thank you.
Thank you, ma'am.
Thank you.
Thank you,
ma'am.
ma'am.
Thank you, ma'am.
Thank you, ma'am.